Hello everyone, welcome to a new live stream, or live coding rather, the first one of 2020. Happy New Year everyone. So for this live coding we're going to look at a regression model, a multimodal regression model. And what that means is that we'll have multiple modularities, meaning multiple different data types, which we'll be treating at the same time. In this case, it will be images combined with some numbers and categories. And the dataset itself, you can find it in the link below, but it's for predicting prices of houses. And for that, we will use the image of the house together with some metadata of the house. I'll look more on the exact dataset as soon as we jump into it. So, well, actually, we can start by looking at the dataset straight away. So let me open it up in a new tab. And this is the dataset we're using. You can find it in Kaggle. You can find it also if you go into the public tab in PerceptiLabs. And as you can see here, we have a few different properties of a house. We have where the house is, so which city it's in. You can see number of bedrooms, you can see number of bathrooms, square foot, and finally the price. So our goal here will be to use all of this information to predict the price. And we also have one here, which is the image ID. So we'll be using these images as to help us predicting the price. So that's how the dataset looks like. For this case, I modified it slightly. I removed the street. I didn't see too much repetitions on the streets, and I thought the city was of larger importance. We automatically encoded the city inside of PerceptiLabs, so I removed n cities. And finally, I made two different datasets, one with a full size and one using just 5,000 samples. So it's a little bit smaller and easier to handle, easier to build a first model out of. All right, so let's jump into PerceptiLabs and see how we can build a model out of this. So I already have it open here, and we'll just jump in and create a new project. We'll choose multimodal, which well, is exactly the type of problem we want to do in this case. You can also use multimodal just to select a CSV file, even if it's not technically multimodal. But in this case, I'll just choose the smaller data set, the 5,001. And we can then go into the data wizard, where we'll see exactly how it looks like. And as you can see, it's the same as in Kaggle. So we have the image ID. I just added the images inside the folder images. We have the city and all the other good stuff. We already have some recommended types here. And we want to change the city to categorical. It recommends tests because there's so many of them. I'll change this over here. And then we can start assigning what's going to be inputs and what's going to be targets. So we have all of these going into the model, and the target is of course the price we want to predict. Last thing we want to do is we want to do a little bit of pre-processing. Namely, we want to normalize the square foot to get it into a range, keep it a little bit lower, easier for the model to deal with. The price we don't touch, as we wanted to predict the full price, not a normalized version of it. And the image ID, or the images rather, we'll resize to make them a little bit smaller. Again, easier to train, easier to handle. And that's everything we need to do with the data. So we'll create our model and we should get something recommended. All right, so first thing we're going to do is to zoom out a bit and place this one so we can actually see everything. So here we have all the inputs, which correlate to, well, everything we assigned as input in the data wizard. And you can see how some of them have a dense layer, some have 2, some have nothing, or one has nothing. How we're going to do this is we're going to take every input. We're then going to pull the data through some encoder, or rather some neural network, to encode the data. Bring it down to a dimension of 128 or 10, so that we then easily can concatenate all of this information. And then we want to add a little decoder, or something which can take all of this information and try to predict the price based on that. And then finally, we'll have the output layer, or output component, which gives us the actual price. So that's the general strategy for these multimodal models. You'll have for every input, you'll have an encoder, and for every target, if you have multiple targets, you'll have a decoder. And in the middle, they'll just get merged together and be kind of a shared pool of knowledge. So I'll go ahead and remove all of this, and we'll build that up from scratch. The standard recommendation probably works well, but we'll build something a little bit more custom for this one. So starting with the images, we can just use the VGG. We know VGGs are good at encoding and processing images, so we'll throw that one in. And after it, we'll add a dense layer, which will act as the encoded data. Or the output, rather, will act as encoded data. And then we'll connect that to input 1. So what happens now is we take the image, we push it through the VGG, we get a encoding of it, but a little bit too high dimensionality, higher than we want. And we then add a second dense, or an extra dense layer to the end to encode it down to more comfortable size. For all other of these, it's pretty simple information. So all we're going to do is just add a single dense layer for them with 10 neurons. And I'll change all of this to ReLU as well. ReLU in general works really well. And the only time mostly you want sigmoid, which is the more common other one, is when you use images. So we'll just swap all of these over to ReLU. And there we have the last one. Okay, we can see that the merge component no longer has an error. Everything is merged correctly. If we look at it, we concatenate it on, well, we only have one dimension to concatenate on, so that's the one we're concatenating. And what that means, essentially, we just add these after each other. So this one, and then this, and this, and this, which is why you can see a big dip in this one. That's when all of these single dense layers come in. So we could now just take this merged information and pass it through this single dense layer as we have it right now. I do worry a little bit that a single dense layer won't be enough to predict the price accurately from this information, from all of this encoded information. So what we'll do instead is just throw in one more dense layer here to add a little bit more complexity to the model. All right, and there we have our model. This takes all our inputs, it encodes them, it merges them, and then it decodes all of that information into a single price. So if we take and save this and then start running it, you can see how it actually performs. In here, we just need to be careful that the loss is quadratic. In general, you want to use quadratic for regression models and cross-entropy for classification models. So swap that over and then start running it. Now I did run this a little bit earlier and I got some strange results and looked into the dataset. And it turns out that there are some peculiarities in the dataset. So we might not get the best result out of this. We'll get decently close, but there are things like bathrooms which are classified. You can see there's 21 different types of bathrooms. So they're classified as 3, 3.1, 4, 4.1. There's one category with 36 bathrooms apparently. But the focus here is more how the model is built and how it actually runs, and or how you would build a multimodal model like this. And you can see that the prediction versus ground truth can be a little bit deceiving because it's just a single sample, but it still gives a decent feel on how close we're getting with our predictions versus, well, our labels, or where we want to be, the ground truth. So we're in general predicting within $200,000 of the actual price, which reflects against the mean absolute error pretty well, which seems to be around 250 for validation and 130 for training. And at this point, we're probably overfitting a little bit, seeing how the loss for training keeps going down and validation not really moving. We then also have the R-squared. R-squared is a different performance metrics for regression models. So when looking at regression models, you probably want to look at mean absolute error, mean squared error, which in our case is the loss. That's different word for the quadratic loss we're using. And R-squared. R-squared tells you if the variance of your prediction, how well they match with the variance of the dataset. If you have very high R-squared, it means that all the variance you're predicting is accounted for by the dataset. Meaning if the dataset is not usually just a straight line, you probably have a variance of plus minus 100,000, for example, dollars in this case for houses, which probably should be the same price. This variance will obviously get reflected in the model, but if the model fully, if the only variance the model has is that variance which is in the dataset, then we'll have an R-squared of 1. As close you get to 0, the variance is just going to get worse and worse, where yeah, you can even go negative, at which point you're going to be predicting values way outside of where the bounds of what you actually want to be predicting them. In this case, we can see the training R-squared is high. We're fitting, the training dataset's fitting really well, but the validation, not so much. It's around that 0 point, which is quite bad. However, again, the data set does look like it's a little bit strange here and there. But at least the model is fitting on the training data set. You could argue overfitting on the training data set, but it's not actually getting worse validation. So I won't say it's overfitting, it's just fitting it really well. And yeah, taking another look at what we actually predicted here, we can see that we, for a house which costs 965,000, that would be this house, we predicted 1 million that it would cost, a little bit above 1 million, which is not a terrible prediction. That's pretty decent. So all in all, it seems like the model is predicting it fairly well. I'm gonna skip the evaluation step because we still have to add in a way to evaluate regression models. Most of the information you need to see is already here. You're going to want to look at the R-squared and the mean absolute error. And we can try deploying it real quick. I tried deploying it to Gradio before and it didn't quite like it. But I think that also was because oh, okay. We'll need to do a quick update on that one before we can deploy it to Gradio. But that's the model for the smaller dataset. That would be how you build a multimodal model with different encoders and summarize all the information, decode it, and get a price out of it. Since we have a little bit of time left, we can take a quick look at how this would look like on the larger dataset as well. And it should go a lot faster now since we already built it once. I think the validation of it, it got as good as it was going to get within about 5 epochs. So we shouldn't need to train more than that. So we'll be training a bit faster this time as well. And here I'm just going through the same steps as I did before. We changed the city to categories. We don't want it to be text. We're changing the image size to 64 by 64. We're normalizing the square foot, and we're not touching the price. And this time, just for fun, we can try a smaller encoder on the images. The one we were using before, the VGG, is pretty complex after all, and we might not need that much complexity. Maybe just finding the boundaries and the size of the house would be enough. Maybe the color. So let's try a simple 2 or 3 layer CNN on the house and see if that's enough for it to run well. Convolutional, you just hold shift and press, and it will keep placing them for you after each other, making it really convenient. And after this last conv, we're going to need a dense layer again, just to have some encoding which we can compare with the other ones. General rule of thumb, how to think of it, all of these all of the outputs of these encoders needs to be able to get merged together. And then we can increase the feature maps a bit. So it follows the ×2, so we have 8, 16, 32. And actually, let's make this one a bit smaller as well. That's half it compared to what it was before. We'll swap this over to Relo. And then start adding these dense layers. And we'll connect everything up. And finally, we can build the decoder. And thank you very much for the words, Dakota, and thank you very much for watching as well. It's great to have you here. I'll build the same decoder as last time. Okay. And then we're ready to run this one again. Remember to swap over to quadratic, and let's run for 5 epochs. See how that goes. We now have more data, a smaller model, and running a little bit fewer epochs. Thank you very much, VCC. All right, so this one is looking decent. Again, don't stare yourself blind on prediction versus ground truth. It's just for one sample. The mean absolute error, though, we can stare ourselves blind at if you want. That one's already dropped down to about where it was before. That 250 validation, we're getting close to it, or 260. And the R² is a little bit below 0, but honestly not a huge difference from last time either. So we can see if there's any huge improvement on the validation before we or for these 5 epochs. But if it's not, then it's probably as good as it's gonna get with this model. One way to zoom into the loss is you can do like this, and then you can see the loss during one epoch. What you see here in the overview is just the loss for each epoch. I believe the end loss, no, the average loss for each epoch. And here is all the iterations losses. And had a question from Cal if the last layer is softmax. We actually, the last layer is just a normal dense and has no activation function on it. So it can output as high or low values as it needs. But to come back to the training, it's not overfitting. The training loss looks about the same as the validation loss. but it's not really improving. The training is, but not the validation. So I think we can call this about as good as it's gonna get. We can train for a lot longer. We're probably gonna get better training, but not much more than that. So the conclusion? The smaller CNN seems like a decent alternative to the VGG, at least at a surface level. Another question from VCC is if some people normalize the target variable. It depends a lot on the target variable. I should be careful, or I would argue to be careful with normalizing the target. Usually you want your model to output what you actually want to have out of it. So if you're targeting dollars, you probably want to have it output dollars rather than a normalized version of it. The trick with you can always unnormalize it, but it doesn't really account that well for outliers. Or maybe it does. It's to get just the raw output from the model. It is often the safer bet or the more normal one, but you can certainly play around with trying it to normalize it as well. And the second point which you made, that it can help comparing MSE, definitely can. In this case, we have quite a large range on the input value. So normalizing it, getting it, would certainly help to be able to compare the MSE, and it might also help the training when the values aren't so ridiculously high. Since remember that the gradients need to kind of catch up and adjust to this high variance and high output. And we can see that through both the gradients and the loss. If you look at the loss, we're up in, what's that, billion? 180 billion. It's quite high. And if we look into a component and look at the gradients, you'll see here as well, they're in the they're in the thousands or millions, hundreds of thousands to millions. So from that perspective, it certainly would be better to normalize it. I guess the only suggestion I can give is to try it out. Try one with normalizing, try one without it. See which one, see if the normalizing performs well on unknown samples, even far outside the range you trained on, when you unnormalize them. And if it doesn't, you have your answer. All right, but we're coming to an end of the live coding stream. I hope I gave some insight, at least, VCC. Got another question from the code. In my understanding, with the normalization of the target variable, one must also ensure that data is normalized based only on the data in the training set and apply this transformation. Does PerceptiLabs accomplish this? Sorry, we have a few transformations. I'm thinking if I have a good answer on that one or not. We definitely don't touch the test data set when we do the transformation. We might transform the validation set, although I can't. I'll need to look that up and come back to you. If you're in our forum or if you're in our Slack, just ping me and I'll reach out to you when I have a better answer. Okay, last 2 questions before we're stopping. From Mr. Ontolog. Without normalization on the target, MSE would be dominated by the large numerical values, wouldn't it? Or it would give fitting, say, higher values. It would be fitting, but it would be fitting to higher values. So it's definitely possible. There's advantages to keeping it within, well, 0 to 1 if you normalize it, or -1 to 1. For sure, you won't have as large gradients and you won't have as large losses. But as you saw here, even with large gradients and losses, our prediction still comes up and comes close to ground truth. So it's very possible that both alternatives are working. I've seen some examples of people normalizing their targets and it not working out, which is why I'm a little bit hesitant to it. But it's always worth trying out. And the last question from Cal Mashal. For regression, is neural network the only option PerceptiLabs offer? PerceptiLabs is very targeted towards deep learning. So we only really have deep learning components, such as dense layers, convolutional layers, and a few public datasets. So we don't have any clustering or L1, L2 regression or things like that. That being said, we do have custom components, and you could probably hammer something. It's plain Python code, so you could put something cool together in here, which accomplishes the same thing. If you do that, let me know, because that's really cool and I would love to see it. Alright, but thanks a lot everyone for watching, and this is Ian Dakota. I'll see you guys in the forum, and we can pick it up from there. Take care everyone, have a great day or evening, and hope to see you next time. Bye!